Okay. So first of all, good morning, Soad. Good morning, Jayla. Good morning, Vivian. Good morning, Alyssa. Good morning, Charlie. Good morning, Noel. And hi. And good morning, Rydia. Okay, good to see you all. We will get rolling here. Good morning. Good morning. Sorry, good morning, Lakshmi. Yes. Okay. I'm okay. I'm a little rattled, but yes, it's good to see you all. I'll tell you what I want. We don't have, I want to get to business. I think we are mostly about business today. What you might have noticed. So this is my understanding. I believe we have today's class. I believe we have class on Wednesday. I believe we have class a week from today, and I believe that's it. And definitely please stop me if that's wrong. Excuse me if that's wrong, but yes. Okay, thank you, Jayla. Totally appreciate it. And thank you for how fast that was. Okay, so I've mentioned before, so I want to start, close down shop, so to speak, in the best way possible for everybody's academic success. I mean, so I've mentioned that the way that you're going to take a final exam is the same way that you took the midterm exam. Of course, we have to do it faster, but I mean, you do and I do. So it's going to be shorter and it's less material. Hopefully it's substantially shorter and substantially less material. Again, hopefully most of us, you and I, have done the hard, hopefully we're past the hardest part of this semester. And now hopefully we're all trying to tie things together to have success. So what I'm taking too long to say is that approximately Tuesday, the 14th, i.e. a week from tomorrow, approximately 8 p.m. that night, I will post what will be the final exam. And then you'll have till approximately the following Sunday night to do it and turn it around and hand it in via Google Classroom. I say approximately because I want to still cover myself. I will tell you definitely precisely in a few days, like as we get a little bit closer, but that's the basic time range. And you'll see, hopefully, that as of about 10 minutes ago, I put something in Google Classroom. In fact, I'm going to ask for confirmation of this. Wait, let me just see the chat. Oh, yeah. Okay, cool. Hopefully you can see in Google Classroom that I put a practice document for that final exam. Again, the practice document is going to be very, very similar to the real thing. Also, any changes I make to the practice, any changes that I need to make to the practice document will be to make it more realistically like the real thing. Any changes that I make to the real thing will be to cater it more directly to exactly where we land before we get there. In other words, I want your final exam to be an exam of material that's appropriate to what you've actually studied. So everything I'm saying right now is to cover myself that changes and updates will still occur in this final week that we have together. But so that you can prepare, basically there's a document in your Google Classroom now that looks a lot like what the final exam will look like. From here on in, all that I'm going to talk about, like today and Wednesday and Monday, is stuff that's on those pieces of paper. I'm just basically going to try to prepare you for your final exam the next 3 days. And at some moments, it'll feel clear that that's exactly what I'm doing. At other moments, it won't feel like, it might feel like I'm saying something that you don't understand how it has to do with those documents, but then you'll see when you do. You'll also notice, hopefully in that document that I just put in Google Classroom for you, you'll see that there are solutions in there. So the idea is that, quark forbid, like we could lose our internet connection right now, or like you could have a whole family conflict right now, or I could, or something. But in principle, for the next week, you've got basically the questions and basically my idea of how to answer those questions that you can use to practice and prepare for our final assessment. I am going to ask you to spend whatever time you have over the next week looking through that thing and trying to understand it and develop questions. It may not be immediately obvious right now how to do it because we still have a week and all of that, but I'm going to be trying to answer questions for the last days that we have. Starting today, I'm going to talk to you about stuff that you need for that document. But after today, hopefully what I say will be driven by your questions that you will have come up with at home. Hopefully this makes some sense. I'm going to pause for a second. First of all, can I just confirm, do you see, in fact, I better check myself, but can anybody confirm, do you just see the practice document in? Yes. Okay, great. Awesome. Okay. And give me 1 second. I have to fix something, but that is great. Okay. And I'm going to caution you again right now. Again, like this is all meant to hopefully make your life better, not worse. It's meant to decrease mystery, not increase it, blah, blah, blah. But I also just want to warn you and admit, like if I were in your position and I open that thing now, aspects of it might look intimidating right now. Aspects might look like things that I think I'm supposed to know, but I feel like I don't, or something like that. I get it. Like, the point is, I don't necessarily believe that you should not believe that you were expected to sit down right now and take that thing right now and rock it and have no problem with it. We still have a lot of class time left before the end. So don't think that. Don't, like, on the other hand, if you're looking, you're like, oh yeah, I get it. Okay, this is lab 4 and lab 5. And even though I don't really still understand lab 4 or lab 5, I get how this is, I get how if I did, this might start making sense. If you're feeling anything like that, you're right. And so we're going to try to put this all together over the next 3 days. Now, hold on, just give me one more pause. So you can like leaf through it for the moment while I just check one more thing or two more things here. Right. Right. Okay. One other thing that is hopefully clear in there, and I hope this was clear from last time from the practice exam. Hopefully it is clear that you do never, this practice exam is for practice. Hope you will hopefully spend time trying to deal with it on your time the next few nights. The next sessions in between classes, you will hopefully have it in front of you as we do class the next 3 days. Again, please remember, sometimes I'll be saying things in class that aren't immediately obvious why they're connected to that, but they are. And sometimes I'll be directly dealing with that, but hopefully you'll have it with you and all this kind of stuff. Just please understand that I do not expect or want you ever to try to turn that into me. That document is for your practice, your like advanced notice. And please understand that everything I'm saying right now is a little bit approximate, a little bit rough drafty, like both the document itself and my deadlines, all that is a little bit still subject to final confirmation. When I give you final confirmation, I'll say that's what it is. Like, this is the final version. This is a final date, blah, blah. But right now, everything's just a little bit, still a little bit work in progress. I'm going to fix one other thing, and then we are going to get talking about it. But you can leaf through it right now and just let me know if anything immediately strikes you as confusing, or any of the logistics of this strike you as confusing. Okay. One last pause. Okay. Hopefully, all right, I'm just looking at, all right. Oh, chat. All right. Sorry. I know I'm all fakakada. Oh, the chat is yes. Okay, great. All right. So you all have it. That's great. I'm going to start like doing some actual physics right now. Again, but please stop me at any moment. What I'm going to do now, just to be as clear as possible, I'm going to do a small physics problem right now that is not in those sheets. Okay, this is like a backup, like it's an example of how to divide up force vectors into force components in order to apply F net equals ma and solve a Newton's second law problem. So what I'm doing now is like a preparatory problem that enables you to understand the main problem of the exam. You won't, the thing I'm about to do, I highly encourage that you take notes. I highly encourage that you understand it. It is preparatory, the thing I'm about to do now, for really understanding frictional inclined planes, right? I mean, so to back up one last way, like your whole lab 5 was about a frictional or a rough inclined plane. Last class, we talked a lot about the friction aspect. The thing we haven't really dealt with directly as a lecture group is how to really deal with the inclined plane aspect, i.e. how really to deal with the angle and what's going on with the angle and what's going on, how that affects gravity and everything. Now, and again, I know that you've already been working through this in your lab and being forced to work through it. So we're putting pieces together from different sides, trying to create a whole. So what I'm going to do now is try to teach you really how to deal with the angle in a simpler problem that on which inclined planes and so forth are based. Okay, so please follow along and maybe have your practice exam next to you, but don't look for an explicit, obvious appearance of this on any of the pages quite yet. Okay. Okay, so here's the situation that we're going to do today, and this will probably take us all today. Okay, and again, well, so here's this, and this is all. If you can follow this and understand this, I think it'll make the whole rough inclined plane that you're being asked, that you were asked to study in the lab, and that you're going to be asked to sort of look at from different perspectives on the final exam. It'll make it much more straightforward. You'll be able to separate all the issues out much better if we look at this first. So what is this? This is a block on a rough horizontal surface. Okay, this is a block on a table. Sorry, someone's here. So, the table is horizontal and the table is rough. The table has friction. So as per our discussion last Wednesday, we're given two coefficients of friction to characterize the table, one coefficient of static friction and one coefficient of kinetic friction. This is the way all rough surfaces are characterized. We have one coefficient for each different type of situation. Each coefficient will work by itself. They never operate at the same time as each other. We're going to see in this problem how they function. Anyways, we've got a table that's rough. It's characterized by a static coefficient of friction of 0.7, a kinetic coefficient of friction of 0.4. We've got a block whose mass is 3 kilograms. And we're imagining that we're pulling this block toward the right, but at an angle. We're pulling it with some string, let's say, some string that has tension in it, right? So this is, it's like a string around a package or something like that. And we're pulling up the string at an angle with respect to the horizontal. An angle that's specified here as 30 degrees above the horizontal, right? So that's how slanted the string is. So we're given all this information. First, in the diagram, I've written them as letters just to show you that the actual values of these properties won't change how we do the problem, but those are the properties that we need to know in order to solve the problem. But then just the numerical values themselves are written off to the left-hand side. Now, on the next page, I'm going to ask questions about this. Hold, but 1 second, someone's just joined us. Just quick. Did someone join? I thought someone just joined us. Hold on 1 second. Oh, no. Okay. We just had like an intruder. Okay. Okay. Sorry, one other thing. I just want to change one other thing. Sorry. I said that the tension is 50 newtons. I meant 500 newtons. I apologize. So just change the tension to 500 newtons. And again, I could flip back and forth the pages whenever you tell me. But the ultimate questions we're going to ask about this situation now, and I hope it's clear. What I just drew was the picture of the situation, like the fact pattern, the thing that we do always need at the beginning of any problem that just tells us what the situation is. We're going to draw in a moment some proper diagrams, system schema, free body diagrams, the vector diagrams. Those are all to help us solve it. But that was just a picture of the facts. Now, I'm going to tell you right now, again, because this is a practice problem, the ultimate questions that are ultimately going to be asked of this is, will the mass accelerate at all? I.e., are we pulling hard enough to overcome static friction? So this is in some ways really a direct practice question about the issue that I raised last week about the nature of static friction, the kind of friction that holds things in place until it no longer can. So very first, whenever we're trying to move something in life, in reality, whenever we try to get something moving, the first issue is like, can we get it moving at all? At all. Like we pull harder and harder until we eventually pull hard enough to get things to overcome static friction. So this is the first question always is, are we even pulling hard enough to get this thing going? Then the second ultimate question is, let's assume we are. I mean, assuming that we find the answer to be yes, then what exactly is the acceleration rate of this block? And I should be clear, in fact, when I say what's the acceleration rate of this block, I mean A sub X. I'm not trying to trick anybody. We've got a block or a package, a box, whatever, on a horizontal table. We're trying to move it along the table by yanking on some rope. The rope is at an angle. Now, the rope is at an angle, partly because I want to teach you physics, but partly because realistically, like that's the way we often do pull things along floors, like for leverage purposes, because we don't want to get down all the way on our knees and crawl with the box. So we attach a rope, right? But why I'm bringing this up is even though we pull at an angle, we're not trying to elevate this block. Let's be clear. We're just trying to drag it across a horizontal floor. If it's going to accelerate at all, it's going to accelerate horizontally along the floor. Somehow all of these angles and diagonals are going to be taken care of in some physics way, and that's what we have to see. But when I talk about the acceleration, the possible acceleration of this block, I mean horizontal acceleration. So now the second question then on this page is, if we can get this block to accelerate, or this package or this box, whatever, if we can get it to slide across the floor, at what rate will it be sliding? Our goal is to get answers to both these questions. If we get an answer to 2 for A, then that will be some sort of constant rate of acceleration, because F net equals ma, and all the forces acting here are constant. So they should all act together to make some sort of constant acceleration. If we find that this package is not moving, that we're not pulling it hard enough to move, then our question instead becomes, well, how hard do we have to pull it in order for it to move? And we'll answer that. Okay, so these are the ultimate goals of this question. Again, this question is like preparatory for your practice document for the final exam. If you can really follow all this, you'll find that the inclined plane itself is just like a sort of slight variation on all of this. So now I'm going to start beginning to solve it. I'm going to break these questions down into smaller questions. Like these are the ultimate things that I'd want to know as a physicist if I looked at this situation. But the way I would go about it is by some sub procedures, which in the context of an exam, we would often ask you. What I mean by that is, in order to do this at all, Okay. And these sub questions that I'm asking now to practice, if any of them happens to be missing from the practice document, if they're not in the practice document, it's pretty likely that they will be added to the practice document before it becomes your final exam. Like, this is a pretty standard procedure for doing stuff like this, and it's what we've been studying. So anyway, so the first thing I always do in order to solve so let me back up again. So notice I've given you a situation with a bunch of numbers in it or a bunch of letters. My ultimate question has to do with acceleration. That's always the ultimate point of any of these kind of Newtonian problems. The ultimate thing is to look at a situation, to look at a given mass at a bunch of ways that it's being influenced and pulled and pushed, and to ultimately figure out what its acceleration must be. Because again, the assumption is if we figured out its acceleration, then that would be the number that we go back in and plug into all the equations and all the work that we've spent all semester churning through. Like, so much of the semester has been an analysis of what you do with acceleration once you have it. And the answer is, once you have acceleration, then you can predict where something is going to be when. Like, from acceleration, you predict velocities. From velocities, you predict places at times. And that is the goal of physics, is to know where something is going to be when, right? So most of our course, I'm just reminding you again to put this in context, most of our course, we spent analyzing what to do once you have an acceleration value. Now, what we're doing at the end of the course is analyzing like where you get the acceleration value from in the first place, okay? And the answer is F net equals MA. But the answer to how to do that, and that sounds very simple. Oh, F net equals MA, end of story. But the real issue behind F net equals MA, or sum of the F's equals MA, in other words, Newton's second law, the real action, the real activity, the real thought, the real head scratching behind F net equals MA comes from, well, what do I mean by F net? Oh, F net means add up all the forces acting on an object in particular directions, along particular axes, with particular negative signs, and with all the appropriate math and trigonometry and all that. So where do we get those F's from? Like, if we actually knew the exact F's and the exact negative signs to add up along each exact axis, then we would just add them all together on each axis and get the A. We would say F net equals MA. We would plug in, divide by M, and get the A along that axis. And we would have accomplished our physics goal. The issue, the hard issue for everybody, students, scholar, whatever, anybody doing physics, the issue always is, well, what exactly are the F's that have to be, what are the F components that have to be added together and subtracted on any given axis to get F? And the answer to that, it comes from the diagrams. That's why the diagrams are so important. I know I've said it before, I apologize for saying it again. But so here we go. If I'm going to analyze this problem, if I'm going to figure out what's happening with the friction and the acceleration, I have to first draw a system schema of the mass. So here I go. Okay, here is my system schema. What the M is the dotted circle in the center, like M is my object of focus, my object of concern. I've got a circle for CE, meaning center of Earth, or you could write PE, meaning planet Earth, or you could write EE, meaning entire Earth. But the point is, there's some circle in there that indicates that enormous source of gravitational pull known as planet Earth. Okay, so that's in there. There's a line connecting Earth to our mass saying that the Earth is pulling on our mass. And by the way, similarly from Newton's third law, our mass is pulling on the Earth. Then there's a circle in there for the, okay, so that, and that's always there in every single diagram, in every single system schema, there's always a circle for Earth and one line between Earth and our object saying the Earth is definitely pulling down on our object, and it's definitely there because it's always there, and it definitely gets a line because it's definitely pulling, and we always draw it first because we might forget it otherwise, partly because it's always there, and also because the Earth is the one thing that's pulling on our object without touching it. So we might forget it if we don't draw it in first because it happens to somehow be able to do this pull without touching. But so that's the CE up in the upper right. Then from then on in, every other object I'm going to draw in is only and every object that is touching our mass. So I draw a circle for the string. The string is an object that's touching our mass. I put one line in between the string and our mass. That seems a little confusing. You might even think, well, isn't that line the string itself? No, the line in system schemas, the lines represent forces, pushes and pulls. That line right there between string and mass is telling me, aha, there's an object called a piece of string in the world. That string is not just any old string. It's not just a string that's crumpled up on the ground or loose or something like that. It's a tight string that is tied on one end to our mass and tied on the other end to someone's hand or something. I don't know, whatever. And it's tight, it's tense, it is exerting a force on our mass, a force that we ultimately will come to call tension, but I don't even care about that in this diagram. I just know that there's a string touching our mass, and so it's pulling it. So that's, in my system schema. Then finally, I have a table that's touching our mass. So I draw a table and I connect it to our mass with a line, but this is the other exception, just like gravity. Notice the string is really the only the string is just an object that's pulling on our object. It's actually the one entity in this diagram that's following the typical one touch, one line rule. The string is an object that's touching our object. Therefore, it gets one line drawn in the diagram to represent the one pull that it is exerting. By the time we get to the table over here, the table gets two lines because the table is a surface that is pushing against the surface of our object. And we have said that whenever surfaces push together, whenever rough surfaces push together, they do this funny thing of actually pushing in two ways at the same time. They push perpendicular to their plane of contact. They also create this rubbing, sliding push along or parallel to their plane of contact. Whenever rough surfaces push against each other, because they're rough, they interlock. And so one touch actually generates two pushes. This is true always, but only in the case of rough surfaces pushing against each other. One of those lines represents what we're ultimately going to call the normal force. The other of the two lines represents what we're ultimately going to call the friction force. The whole idea behind this diagram is that we have one line for everything we have one line for every force that we're ultimately going to have to keep track of mathematically in the free body diagram and in the components and all that. So the purpose of this diagram is to generate lines. The number of lines in this diagram literally and precisely and non-coincidentally becomes the number of arrows in our free body diagram. Really, honestly, the purpose of this picture, as stupid as it might seem to many of you, and honestly, it seemed stupid to me for a long time. For many reasons, it seems stupid, but it's not stupid because what it does is to my opinion, it is not stupid because what this picture does, it asks you just to focus on Earth and any objects touching your object. And just by focusing on it, just going, okay, what's touching my object? What's literally directly touching my object? Literally directly. By asking you just to ask yourself that question, it forces you to write down the correct number of lines in this picture. And that protects you to make sure that you count all of the forces when you do the math, and it protects you from accidentally not including things that aren't forces in the math, okay? So the number of lines that we see here is really the purpose of this picture. Last thing I'm going to say about it, notice that's such an important purpose, and it's so easy, honestly, to get that wrong without this picture, that nothing else matters about this picture. Notice I got the Earth flying off to the right, I've got the string down below, and I got the table off to the left. Direction doesn't matter. You could draw the Earth wherever you want. You could draw the string wherever you want. It's just as long as they each get connected to the dotted circle representing the mass, just as long as they each get connected by the proper number of lines. That's the only thing that matters here. We're focusing all of our attention on the number of forces, and we're figuring out what is or is not a force just by looking at what objects are actually touching our object. I know I keep saying it, but again, just always remember that when you go sit down to do physics, the common feeling that we all have is, I know what to do, I just don't know how to begin, right? I mean, honestly, between you and me, that's a very common feeling, right? I get what he's talking about when he talks about it. Then I go down to do it, and I can do it once it's started, but I don't know how to start. I'm here to tell everybody that we all sympathize with that. It's very hard to start a physics problem. That is the hardest part. But the real secret in starting a physics problem has to do with taking diagrams really seriously. They do all the work for you. People don't do them because they seem so stupid, but they're meant to seem stupid. They're meant to do the thinking for you. They're meant to allow you to turn your brain off and do a dumb little thing that seems dumb. And the next thing you know, the proper results are on the page for you. So please take this seriously. Anyway, and notice what it's really trying to say too is there's a string pulling this box. There's probably a person pulling the string, but notice the person's not in this picture. The string is in the picture. The string is counted as an object because the string directly touches the box. But the person and I know that a string is inanimate. I know a string isn't deciding to exert newtons of force on the box or something like that. The string doesn't have muscles. I know that. And I know there must be a person who is deciding and pulling the string, but that's where everybody gets themselves into trouble. People want to put the person into the diagram or something like that, or start counting the person as the important thing, but that's where you get into trouble, because then how is the person pulling on the string? Well, either because they ate their cornflakes that morning and and their mitochondria, which is the powerhouse of the cell, did some biological thing and underwent some Krebs cycle and converted, right? I don't either there's some biological chemical reason inside a person's body that allowed them to actually move their muscle and pull the string, or they shoved their feet against the floor and they leveraged themselves off the floor and then was allowed, there's some reason that the person was allowed to pull the string. I don't know what that reason is. And whatever that reason is, then you're going to have to give a reason for that reason. And if you're not careful and you look for reasons and reasons and reasons, and you really try to think about all this, then the tendency is for all smart people like you guys to overthink and never know when to cut the madness off. So the whole actual idea of this program is we just look at immediate first causes. Whatever's literally touching the mass of interest, that's what's doing the action. And that's all we need to know. So string goes in here. Person holding string does not go in here. Okay, anyway, enough of that. So that's the system schema. So what do we do with this? Now we're going to make a free body diagram from the system schema. And what the free body diagram is going to be a dot representing our mass, and it's going to have arrows, force vectors coming out of it. There's going to be one arrow for every one line in this picture. There's going to be 4 arrows in my free body diagram, definitely. And so here we go. Okay, so here comes a free body diagram of the mass. And again, okay. So I'm going to draw the pure free body diagram. Now here I keep alluding to this. I alluded to this last week and maybe the week before, and I know you've seen this in Lab, but I've never really broken this. Well, I've sort of broken this down, but what I'm going to do is for every force acting on my mass, for every pull or push happening to my mass, I'm going to draw a vector arrow whose magnitude is roughly approximately comparatively captures the size of that force to the best of my ability, and whose orientation, whose tip and tail, captures the actual direction of that force, the direction that that force is acting on my mass. Okay, so note it before I even, so I'm going to draw arrows now. So now we're shifting our concern from number and identity of forces to direction of forces. And notice that the lines didn't have direction because the lines were representing the entire sort of Newton's third law interaction of each force. Like a line between Earth and mass shows that the Earth is pulling down on the mass, and at the same time, necessarily, the mass must be pulling back, pulling up on the earth. That is totally true. And that is captured in the system schema. All those mutual reciprocal relationships are captured in the system schema. But now I don't care anymore. They were there to get me to know, to be confident of what forces are happening to my mass. Now I only care what is happening to my mass. I don't care what it's doing back to the universe, because if I did, I'd have to have like 5 diagrams going on. I'd have to have a diagram of the earth and a diagram of the table. And all I care about now is what's going to happen to my mass. And so I start putting in arrows here, and I label, I should also say, I start labeling these force arrows with proper force names to make the math easier to do. Okay. So one arrow I put in right away is the downward arrow representing the pull of Earth on the object. A pull that is often also known as weight, like that's literally synonymous, right? Your weight is the force exerted on you by planet Earth, measured in newtons. By the way, this was discussed fairly heavily in one of the videos that I did ask you to watch, and I'm really going to stress again that you please watch them. And anytime you show any evidence of watching those extra videos, you submit, you get points. It also reminds you on the final exam to watch them, blah, 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 blah. Because another thing that it says in that video that I don't want to spend too much time saying now, because I think you've seen it, but that an abbreviation that we use for weight, for the force of gravity in physics, is m times lowercase g. Now, I'll just pause long enough to say, you may want to really watch the video, really think about that. We use it, it's so common, it's so frequent, it's important to get used to, but it's also really important not just to skip steps. I'm saying the force of gravity, mg, lowercase g still stands for that acceleration in free fall due to gravity, the 9.8 number. That's just an acceleration. F net equals ma. Forces are masses times acceleration. What we're saying is that if an object were in free fall, the only force acting on it would be its weight by definition of free fall. When an object is in free fall, the only force acting on it is weight. Therefore, the net force acting on it is weight. And F net equals ma. The sum of all the forces on you equals your mass times your acceleration. So if something were in free fall, the net force on it would be its mass times its acceleration. Its acceleration in free fall is g, the free fall number, 9.8. So the weight of any object is its mass times the 9.8 number. The weight of any object is its mass in kilograms times 9.8 meters per second squared, right? So bottom line, and again, please watch the video on this, but mass does not, m does not mean the same thing as g, and m does not mean the same thing as mg, and g does not mean the same thing as mg. Mg is the weight of any object, even, and that's its weight, even when it is sitting on a table or subject to other forces. That's the force of gravity right there is mg. So that's in every single free body diagram, and it always points down. So I always put that in first. Every single object is being pulled down by planet Earth, no matter what else is or is not going on. But what else is going on? Well, what else is going on is anything and everything that's touching this object, just like we just said in the system schema. The system schema told us, for example, that there's a string pulling this object up and to the right, or at least our picture. Our picture says that there's a string pulling up and to the right. So there's a force of tension being exerted by that string, pulling up and to the right. So I draw it in. I'm guessing it's probably a little bit, well, no, I know for a fact that it is bigger. I'll make it bigger, bigger than the force of weight, because I was told that the tension in the string is like 500 newtons. The weight of this object is only mass of 3 kilograms times 9.8 meters per second squared. So the weight is only about 30 newtons. Okay, so we have an arrow going down for gravity. We have an arrow going up and to the right for tension. What else is going on in this diagram? Well, there were 2 lines represented by the push pushes from the surface underneath this block, right? Two lines, one representing the fact that the table underneath this block is pushing perpendicular to the plane of contact. Pushing in this case, in other words, straight up. That is called the normal force, right? The component of push that is normal to the plane of contact. Normal meaning perpendicular. There is a normal force I'll just exaggerate this a little. Okay, we've got the weight down, we've got tension pulling up and to the right, we've got the normal force up. Notice I didn't make this normal arrow equal to the gravity down arrow. It is opposite in direction. The normal force is opposite in direction to the force of weight, the gravitational force. But I don't think it's equal in magnitude. First of all, I do not think that these are a Newton's third law pair. Please remember, Newton's third law says, I push you, you push me back. The action and the reaction of any Newton's third law pair are never seen in the same free body diagram. They're always captured in the system schema by a line. The fact that each force is depicted as a line in the system schema, a line with no tips and no tails, is trying to show us that each force is a symmetric mutual interaction between two objects. Earth pulls me, I pull the earth. But now here, we're just looking at what's pulling on the mass. Earth pulls the mass down, that's an action. Therefore, mass pulls the earth up, that's the reaction. That would be in some other diagram of the earth. Similarly, table pushes the mass up. That is not a Newton's third law reaction to the earth pulling the mass down. Even just look at the English, just listen to the English. Earth pulls box down, table pushes box up. That's not a reaction. One is a pull, the other is a push. They're from two totally different objects. There's no law that says if the earth pulls me down, a table must push me up. If there were such a law, nothing would ever be in free fall. Nothing would ever accelerate. What's happening here is the earth is pulling the block down. That's one thing that's happening. And then independently of that, a table is pushing the block up. That's totally another thing. Okay, they're not a Newton's third law action reaction pair. So they don't have to be equal in magnitude. Furthermore, I'm suggesting to you, I believe they're not equal in magnitude. We're going to see when we run the numbers and everything, and I'm not trying to get ahead of myself, but I'm just sketching these arrows here. But I think that normal arrow going up is going to be bigger than sorry, no, not bigger, smaller. I mean, it's definitely not equal, but I think it's smaller. Sorry, smaller, and I'll tell you why. Sorry, that's my bad. I think it's smaller. And the reason I think it's smaller is because we're going to find when we do components of this diagram, because the table doesn't have to do all the work to support the weight of this object. Like the weight of this object is being supported for sure. It's not crashing to the table. And it's not flying up above the table. It's ultimately, we're going to find the vertical forces are balanced. But look, the tension is doing something somewhat vertical. That tension is going off on an angle. It's going somewhat up and somewhat over. The string is pulling somewhat up on the block. So the string is, no pun intended, picking up some of the slack. The reason this block is supported on a table is to some extent because of the string. The table doesn't have to push up as hard. The string is helping it. So I think we're going to find, so again, these are just rough. I don't care too much about magnitudes in this diagram. What I'm really concerned about is direction, but these are supposed to be approximate vectors. So just to give you a sense so far, this is how the vectors are working. They're in the correct directions and they're comparatively approximately the right magnitudes. There's one more vector that has to go in. I know there's one more vector that's going in because there was 4 lines in the system schema. So there have to be 4 arrows here. The other arrow that has to go in is the arrow for friction. Now we're trying to pull the block to the right and up. So I think according to our lecture last week, friction, whatever kind it is either trying to oppose motion or it is resisting onward motion. Motion is tending towards the right. If there's any other horizontal forces going on, they're to the right. So friction is to the left along the plane of contact. So I'll designate with a lowercase, that's supposed to be a lowercase script f. Okay, this is my free body diagram right there. We're done. And I'm looking at the time. This is my pure free body diagram. There are only arrows in it. The tail of every arrow starts at the dot, which represents my mass. Each arrow is labeled with the name of a force. Like, again, notice in the system schema, what was named was the objects creating those forces: earth, table, string. We were really trying to see what forces were going on, but we couldn't put a force in the system schema unless we had identified an object that was generating that force. Because what we believe in is actual real material objects make forces. Once we satisfied ourselves in the system schema, now we pluck those forces from our knowledge from those lines there. We give them names. The name of the pulling force exerted by a string is called tension. The name of a pushing force exerted by a surface is called normal. The name of the sliding, rubbing force exerted by a pushing surface is called friction. And the downward weight of an object is called weight, and it's often called mg. So now we've got one force vector for each force that's acting on our object. Anything that our object is doing back in response to these arrows would lie in other diagrams that we're not concerned about here. We're trying to calculate the acceleration of our object. So now that is a pure free body diagram. One vector for every force acting in the direction that it actually is acting on our mass. Okay, what do we do next? What do we do with this? Again, the purpose of all this is to have things to plug into the left side of F net equals MA. So we have to go one more step before we can plug things in. F net equals MA is a vector equation. It really is a set of simultaneous equations. F net equals MA really means F net X equals MAX, while independently yet simultaneously F net Y equals MAY and F net Z equals MAZ. It's, in other words, all the forces that added up along an x-axis, including minus signs, produces the acceleration along the x-axis. And simultaneously, yet independently, all of the force components acting along a y-axis produce the acceleration along the y-axis, et cetera, et cetera. What we need here, what we need to do is see a map of all of these force components acting along axes. We don't have that yet here. Like, we've got at least one arrow that's flying off on axes that don't seem to be captured by the other arrows, or vice versa. Like, what we need now is a component diagram. We need to break up certain forces so that all force components lie either on an x-axis or a y-axis. In other words, we need a diagram where all arrows we see are either parallel or perpendicular to one another, so that we can just like literally do the math along perpendicular axes separately. So we need a component diagram. Again, usually exams will ask you for each one of these steps, but whether an exam asks you for each one of these steps or not, the only way to do Newtonian problems is to do each one of these steps. So 3 is draw a component diagram. Okay, and so the logic of this goes back to like lab 3 to extend lab 4, where the whole idea here is physics exists in each axis at a time, independently yet simultaneously, right? Like, we can add north to south or north to north, but we can't add north to east, etc. So what this really means, in order to draw the component free body diagram, and this is where this gets into the inclined plane business and everything. This is sort of the tricky, subtle part. And this, believe it or not, still all goes back to Galileo in the end. It all goes back to the laws of physics are the same in each unaccelerated frame of reference, or in each unaccelerated coordinate system. You have to think of every coordinate system, even down to the simplest idea of think of every x-axis, think of y-axis, think of z-axis as its own little physics world where physics runs according to the same laws independently. What I'm getting at is before we split up, like the step that we have to do here is split up vectors into their components. We have to take vectors and treat them as like the hypotenuses of little right triangles and get the associated legs. And you guys did this a lot before with displacements and velocities in earlier material. I think you know how to split. Many of you, I think, are growing comfortable with splitting vectors into their constituent components. But the reason I have to take a breath here and pause for a second, the thing that escapes a lot of people, and you totally have to do this on the inclined plane, for example, you've got to break up arrows into components that lie along designated axes. The step that's easiest to skip, and yet that is yet the most important, is in order to do that, we have to choose our axes. It's all Galileo, whether it seems like it or not, that we have to choose explicitly, consciously, what our coordinate system is before we break everything up into that coordinate system. The beauty of Galileo is that any coordinate system we pick will work as long as we stay in that coordinate system consistently. But the flip side of that is we have to know which one we're in order for it to work. Because if we don't consciously choose a coordinate system, we're going to unconsciously flip-flop back around from one coordinate system to the other and become inconsistent, like honestly. So I'm saying here we have to choose, we have to break up vectors into X and Y axes. We have to choose what we mean by the X and Y axis. Any choice we make will work, but we have to make a choice, and some choices will work more conveniently than others. You will really see this, and I'm warning you right now, this is the most abstract part. This is really the thing that the final exam is about. The final exam is really about an inclined plane. I know you've already studied inclined planes and stuff in lab. I know that some of you have memorized certain things that happen in the lab, and maybe you're comfortable with them, maybe you're not. But I'll tell you straight up, point blank, that the hardest, weirdest thing about the inclined plane is that all of a sudden mg is being broken up into components mg sine theta and mg cosine theta. Many of you have gotten used to that, but some of you have gotten used to it just by deciding to get used to it and just accepting it on faith. You may remember, many of you, that when you first saw, and I'm talking to anybody that I'm talking to, when you first see anybody write down mg sine theta and realize, when you first realize that they've broken up mg into a sine and a cosine, that is weird. It's unexpected. I'm telling you right now, even if it flew past you in the lab or you flew through it because there was no time or no one explained it, I am saying, if you notice, anytime you've ever written in your life mg sine theta, mg times sine of theta, or mg cosine theta, what you're doing when you do that is you're tacitly assuming that mg is the hypotenuse of some triangle that has two legs, and you're breaking up mg into two components, an x component and a y component. Well, I'm here to really break down that decision for you, because it turns out that's a very good decision to make, but it's a very weird decision to make. And honestly, if I'm boring you, or if you really understand all this stuff already, or if you're looking at the final exam, you'll see that a big part of the final exam, what you're really being asked to do is actually solve an inclined plane two different ways with two different choices. What you're really being asked to do in the final exam is do the work with that choice that you do in lab, but then also start the work all over again and make a different choice and see how they both work out to the same answer, but with varying levels of convenience. What I'm here trying to say, I'm going to show you right now, and again, I do know I'm running out of time, but I am saying deciding which vectors to break up into components and which not is actually worth thought. If it ever confused you for one moment why we were breaking up gravity, you were right to be confused. And you shouldn't just skip that step. You should actually pat yourself on the back. If even for one moment you're like, wait, what? Why did mg, mg points straight down. Why did that get broken up into components? Oh, well, I'm here to say it doesn't always. that is a choice that we made in lab. And I'm here to try to show you how and when to make choices like that. So I'm going to say right now, for example, so I'm getting off, but again, if you ever have any issue in your mind about MG sine and MG cosine and that stuff in lab, that's what this is meant to actually explore and dissect. And we'll keep talking about it Wednesday. And that's what I want to practice with you. But it's not too late. Don't think it's too, or something like that. Like that is the thought worth thinking about. So what happens here? Well, here I'm going to break up vectors into components. Here I'm going to choose my X and Y axes, but I'm going to choose the ones that you might have originally wanted me to or thought that I would. I'm not going to choose the same axes that you did in lab. What I'm going to do is follow the strategy that led to that lab choices. So here's what I'm saying. Here's what I'm saying. Okay, so what I'm just saying here, and I am watching the time, I'm saying the first thing we have to do before we break up vectors into components, we literally choose what we mean by our X, Y, and Z axis. What I literally mean by that, by the way, is like, am I going to say that my X axis is parallel to the floor, my Y axis is like parallel to gravity, perpendicular to the floor, which would be a standard choice that you would just generally expect, presumably. Or am I going to tilt my axis as you do in the lab? In the lab, you tilt your axes and you line up your X axis to be parallel to the actual plane itself. And you make your y-axis parallel to the normal force. Some of you may be remembering what I'm saying or familiar with what I'm saying. I'm saying in that lab, you actually, if you really think about it, you tilted your axes and you said that anything lying off those axes had to get a sine theta or a cosine theta component. We have to make a choice of what our axes are like. Are they rotated? Are they not? And we make different choices for different circumstances. All choices will work as long as we're conscious. That's what it says here. But we have to be conscious and consistent of our choice. And some choices are more strategic, more convenient than others. So how will we choose? Here is the strategy that will never steer you wrong if you understand it and choose to follow it. Here it is. The strategy is okay, very quickly, and I know we have 5 minutes, so I'm going to say this quickly. What I'm saying is the ultimate strategy that's going to, if you're really following this is a subtlety, this whole thing. I'm telling you a strategy now that will lead you to one result here in the problem we're doing, and a different result in at least one way you do the inclined plane. But you'll see in the final exam sort of all a comparison between these two results. It'll look like we're doing two different things unless you understand this strategy, and then you'll see that we're doing the same thing. The decision that we're going to make is we look at any problem, we have any problem at all, this problem, the inclined plane problem, we ask ourselves, in what direction is the object expected to accelerate? Like here, if the object accelerates at all, it's going to accelerate horizontally. In the lab, on an inclined plane, if the object accelerated at all, it would accelerate at a slant. What we do is we choose to line up our positive x-axis with the direction of expected acceleration. Here, and the reason, well, there's actually many reasons for that. Again, this is a strategy. You could like not do this, but then things are going to be even more confusing. There's no law that you have to do this, but this is my strategy. And it's what most physicists do. In this case, why do we do it? Well, one reason is F net equals MA. If we choose an x-axis to line up with A, then the A that we solve for will be as simple as possible. Then all of our work will be solving for an A that actually will take place where we expect it. And A won't have to be divided up into different components with sines and cosines. If we don't line our axes up with A in advance, we're going to get an A on one axis component and an A component on another axis. And so we're ending up going to be having sines and cosines on the right-hand side of Newton's second law before we even start plugging in forces. Like we're going to have a lot more sines and cosines than we would want. That's the simplest reason to do this. You'll sort of maybe see other reasons as we go, but I know we have 3 minutes. So I'm going to say, and then we're not going to solve the whole problem today. As I said, so we'll finish solving the problem on Wednesday or in a video or whatever. But in order to, so I'm saying now for this problem, not for the inclined plane, for this problem, I'm saying I'm choosing then that like my x-axis will look like this, and therefore my y-axis will look like that. Y-axis is always perpendicular to x-axis. So if I divide things into components here, then like that arrow that was pointing up and to the right, that tension that was pointing up and to the right, that has to be divided into two components. Like anything that doesn't lie along one of these axes becomes a hypotenuse of some mini right triangle. And I have to solve for its legs of that right triangle, its vector components. In other words, under this coordinate system, all forces are fine except for tension. Tension, I had to zoom in. I had to zoom in on the offender, so to speak. The tension was the offending force, the one that lied off axis. So I zoom in on it and I get its components. And thus I can make a component diagram. And this is where we're going to stop today. The component FBD, I take these two components of tension and I say, now those two components are simultaneously yet independently constituting tension itself. Like now, instead of tension, which is off axis, I take the X component of tension plus the Y component of tension. They together make tension. I substitute them back into the original diagram. To make my component diagram, I want to end up with all my forces accounted for, but only along X and Y axes. And I don't want to double count anything or anything. So this is my final, we have 1 minute. This is my final picture and we're done. I'm saying then our final component FBD, and we'll crunch all the numbers Wednesday, but component FBD would look like this. MG is down, T cosine theta is like that, T sine theta is like that. Normal force is still in the diagram. Friction is still, sorry, make that shorter. I don't know actually how long this been. This is my final, this is my component free body diagram. Now I'm ready to do math. Now I can do math. I'm not going to do it now. Class is over. But I'm saying, notice there were 4 lines in the system schema. Then there were 4 arrows in the pure free body diagram. But then I chose my axes and I decided, oh, of those 4 arrows, one of them is an offender. There could have been a million, but there happened to be one that was off axis. So I broke it into 2 components. So 1 became 2. So now this diagram has 5 arrows in it. None of the other arrows got messed with or substituted or anything. This is, and there's no numbers in here. This now prepares me to do the math, and the math will be easy if I've done all this right. But that's all for today. Thank you for paying so much attention. We'll just like pick up on this on Wednesday. I'll hang out for 1 second, but you've been very good people. Thank you so much. Thank you. Thank you. Thank you. Awesome. Thank you.